tools to do that. Okay, and so I mean this is of course like the previous set of results, is a very rich and extensive theory. And what I'm going to do today is start providing you with a framework for solving a subclass of these using some simple first order methods. Okay, so the idea is going to be based on the following. Let me just augment this with the. So the idea comes from simple projected gradient methods. So if you look at, if I gave you a convex optimization problem, so suppose I gave you this problem. So this is a convex function over a convex set X. So now if you imagine that this is the set, okay, this is the set, and these are the contours of the function. So the optimal solution is somewhere here. Okay. Now what happens is that when you start a projected gradient scheme, the scheme is based on the following. Okay, and I'm going to explain every part of this. So this is for optimization, and I'm going to tell you how it changes for VIs. So what you do is gamma k is a step length, xk is the iterate, and you move along the negative gradient direction because you're trying to in some sense improve. So suppose I gave you a point here. Okay. Now if the contours are like this is the gradient, this is negative gradient. Okay, let me take a point here because I want to show some part of the projection. So if I'm here, suppose x naught is here. So what happens is I take a step like this. Okay. As soon as I take a step, I leave. It turns out I leave the set. If I leave the set, I project back. So this is the projection. So I project back, and this new projected step is x1. Okay. Again, now suppose it turns out the contours are outside, I just go out and I project back. Okay. And I keep doing this, and this under some conditions you can show that you converge to the solution. That's the simplest gradient update scheme called the projected gradient update. The only difference for VIs is instead of using, remember what a VI is. So the solution of a convex optimization problem, if it's on the boundary, if it's in the interior, it's just basically the gradient is 0. If it's on the boundary, remember what the statement is. You want to make sure that the gradient lies in the normal cone. So you need 0 in the normal cone. That's one way to look at it, right? Similarly, the VI is I want an x such that it satisfies this equation. Same approach. The only thing is instead of using the gradient, you use the map. Okay. The reason why we use the term first order is it's inherited from convex optimization. You only need first derivatives for the gradient, you just need evaluations of the map, as opposed to a second derivative method where you need the Jacobian on the map, like Newton type methods. Okay. So now, so the scheme that we are going to consider, and where do we motivate this from? So you remember that one of the things we started with was this natural, what was an equivalent representation of x being a solution to VI, xf? Well, it was that x was a solution to the natural map, right? So x solves VI x comma f if and only if x minus the projection, or x is equal to the projection, right? Now you can use this to motivate a scheme. You just say, oh, I figured out what this is. If it's not equal to xk, I just project it, and I update my new xk based on that. So it's just a direct, but I use a certain step length. Okay. So the standard projected gradient update requires you to just proceed through this iteration, given an x naught which lies in the set. Okay. Now this scheme is referred to as first order because it only requires evaluations of the map as opposed to evaluations of the Jacobian of the map. Okay. Okay. So now what are we interested in when you have an algorithm? We're interested in, so let me just tell you from an algorithmic standpoint, whenever somebody tells you about an algorithm, there are lots of questions you should be asking. First of all, can you show that the algorithm converges to a solution or equilibrium of the problem as k goes to infinity? So asymptotically, does the scheme produce a sequence that converges to a solution? The second is, can you show, and this is not always available, can you show that this diminishes at some rate? Maybe the rate is 1 upon, say it's some beta upon k raised to, some k. So basically this is like it's called a sublinear rate. So as k goes to infinity, this goes to 0. What do you know? You know that if k is 1,000, this is no greater than beta over 1,000. And you know what beta is. Beta is something you can evaluate. So before you start the algorithm, you know the worst case behavior of the algorithm. Okay, so that's one of the things I want to aim at. Okay, so we're going to start proving when is it that projected gradient schemes allow us to claim these types of properties. And can I tell you what this rate is? So this is called the rate, and this is called global convergence or just convergence. Is that clear? Okay. Okay, so the first statement requires that the map be strongly monotone and L Lipschitz. So what is a strongly monotone map? We've talked about it before. For all x and y in x, fx minus fy transpose x minus y is greater than eta times x minus y the whole squared. So this is the strong monotonicity property. And if eta is 0, then you just have monotonicity. A map is said to be L Lipschitz if, so what does this mean? This just means if I change the map, the value of, I'm evaluating the map by x to y, then the difference between this changes by no greater than L times x minus y. Okay, so this is a stronger form of continuity. Okay, so Lipschitz continuity is stronger than continuity. Yes. You had a question, Malabir?
Yes.
Yeah.
And L is specified constant by us, right?
Yes. No, not by us. It's something that comes from the problem. So for instance, let me give you some examples. So actually this is a good time. This is some examples I want to do because I want to make sure that for those of you who are solving game theoretic problems, know how to compute these constants. So let's take some examples, okay? Let's take the case of a Cournot game. So in a Cournot game, each player solves what? Let's assume that they solve Ci xi squared, quadratic cost, and their let's assume this is the problem, just to start talking. Okay, so now this is for all I. Okay, so what is f of x here? F of x is the gradient of each of these. So it's Ci xi, sorry, let's start from the beginning. C1 x1 plus, and I'm going to assume p of x is a minus the summation of xi. Okay, so this is C1 x1 plus x plus x1 minus a. C2 x2 Does everybody agree? All I've done is taken the gradients of these and stacked them up. Clear? Irina? Clear? Okay, so then what I can do is I can write this in the following fashion. I'd like to write it as a matrix times something else. Why? Because this is an affine map. It's one of the benefits of Cournot. So I'll show you why that helps you. So what you're left with is diag of C plus I plus E transpose times X transpose X, yeah, minus A times E.
Well, if you have capacity constraint, still you
I can keep it inside. If I have a capacity constraint, I'll just keep it here because I'm trying to show monotone. Because what I'll do is, if I had any constraint, suppose I have any other constraints, I can just write these as xi lies in capital Xi, where that is xi is defined as the set of xi such that. So I put all the nasty constraints, not nasty, complicated constraints in xi.
and you write the cap just in primal.
In just primal variables, because I can assume that I'm going to project on these. Okay, so I don't need to worry
We
about.
can do it if we don't have shared constraint.
If you have shared constraint, you do shared multipliers, then you can still do this, but you'll need an extra player for the price, and then you lose monotonicity, strong monotonicity. You'll just get monotonicity. Okay, so what you're going to get here is this times x. So I want to make sure everybody understands how I've got this expression. So diag of a vector is a matrix where, okay, so when I say diag of C times x, I get exactly this. Similarly, I can write this as I plus E transpose times x, where E is the column of ones, and minus A times E, which is the column of ones. Okay, so if there's something that you don't see in this, tell me and I'll go through it again. Okay. Okay, so now I want to show, I'm going to call this fx. I want to show two properties. One is I want to show, let me just keep that up here. So I'm going to first show that fx is Lipschitz. So this is Cx minus Cy plus I plus E transpose x minus y, and the AE cancels. Okay, all I've done is I've taken the f of x minus f of y. The AE cancels. Question, Priyanka?
The plus sign is missing in a
Oh, yeah, there's a plus sign. Because I erased that x. I had to put the x and I missed it.
What is the minimum limit for xi? I didn't get that.
Xi is just 0. I could put anything. Okay. So does everybody see this? So this is equal to C times x minus y plus. So now what you can do is, remember, u plus v, the norm of u plus v is less than the norm of u plus the norm of v. This is triangle inequality. Okay, it's the triangle inequality. Okay. Now this has some value. The norm of I plus E transpose based on the number of agents, it has some value. Let's call it, it's some value greater than 1. It's called beta. And this is, I can bring the C out because C is a scalar. Oh no, C in this case is a vector, I'm sorry. This is just norm C times x minus y. How do you do that? So that is basically, so you can just use Cauchy-Schwarz for that. So okay, so what you get is, it's called the C bar, and you're left with C bar plus beta times x minus y. Okay.
You have this norm C.
So what I was a bit loose here. All I'm saying is that this is C is a, look what C is in this case. C is diag C, right? It's some, so then what you have is you have A times B is less than norm A norm B. Okay, so now remember this is A here is a matrix because you have capital C times U, right? So now what you have is, so what you're going to get is the norm of diag of C, right? So just a norm of this vector. So the Lipschitz constant is this. Okay. Now, not always can you go and analyze this, but that's why it's useful to have some structure in your problem, because if you can get a relatively tight constant on the relatively tight Lipschitz constant, because you just want some constant. I could come up with 100 times this. But you see that if your Lipschitz constant is large, your step lengths are small and it affects the progress of your algorithm. Okay, so it would help to have something decent. Ideally, you don't want these constants in your algorithm because you need to go and estimate them. The second thing that you want to do is compute strong monotonicity. So for strong monotonicity, the same mapping, C times x minus y plus I plus EE transpose. So this is f of x minus f of y. So this minus y transpose x minus y. Okay. So this is f of x minus f of y transpose x minus y. So this is equal to this. And now what you have is, oh, I'm sorry. So this is equal to C plus I plus E transpose norm x minus y squared, because x minus y transpose x minus y is x minus y squared. Okay, and now so you have to be careful here. So actually here, I'm sorry. So now you've got this, so matrix times, so remember what you have here. What you have here is this thing transpose. So what you're going to get is x minus y times some b, let's call this b, transpose b transpose x minus y. And this is a symmetric matrix, because C is symmetric and I plus E transpose is symmetric. So this is greater than the minimum eigenvalue of B times x minus y squared. How do I know what the minimum eigenvalue of this is? C plus I plus E transpose. Well, this is a positive semi-definite matrix. This is a positive definite matrix with the smallest eigenvalues 1, and this is a positive definite matrix. The smallest eigenvalue is some epsilon. So we know the smallest eigenvalue of this is going to be 1. So in this case, we know that lambda min b is at least 1 for this problem. So this is the strong monotonicity constant. This is the eta. So now I've shown you how to compute the eta, and I've shown you how to compute the L for a particular problem. Okay?
Could you please repeat the last step?
Yeah, I will. 1 second. Just get back in this thing. So the last step is, get rid of this. The last step comes from here. So this is from, if I gave you a matrix, a symmetric matrix, and I asked you x transpose Ax is greater than lambda min norm x squared and is lambda max x squared. Okay, and so this lambda min just comes from the smallest eigenvalue of A.
If you only need strongly monotonicity, you could easily check just the Jacobian, right?
So that's exactly what, you could check the Jacobian, but that's exactly what you end up with. The Jacobian of this is this matrix plus C.
Yeah, which is positive definite, so it's extracting one.
If it's positive definite, but if I don't have a bound on the smallest eigenvalue, it could just be positive definite, and I may not be able to get a clean bound. But I need to have a clean bound for this. I need this eta. Right? Okay, so now, so our first result is if the set X is closed and convex, I don't need compactness, and F is a single valued strongly monotone Lipschitz continuous map, I'm going to consider the sequence given by that projected update. And if I choose gamma as a constant such that this holds, and I'll show you, that you can choose gamma as being, I can choose gamma so if I want to get this to be less than 1, you can choose gamma to be something of the order of eta over L squared. That works. Okay. Anyway, so you can show that xk converges to x star as k goes to infinity, and you have that norm xk minus x star is less than q raised to k, where q is less than 1. So this abides by what is called a linear rate of convergence, right? So this is fast. So that's why when we say sublinear is poorer than linear. So a linear rate of convergence because of the fact that q is less than 1. Okay. So I know that not all of you are going to be sitting and kind of developing these algorithms, but it's important to understand at least what their basic, how you prove something for a fairly straightforward scheme like this. So I want to go through this because it will expose you to the analysis, and I don't think it's too, but I won't do it on the board. I mean, I won't do it I'll do it by hand, so that when I do it by hand, you'll see how we do it, okay? Okay. So whenever you analyze these types of update rules, the proof technique is quite similar. Right? So once you get used to one of them, most of the other ones start falling into place without too much difficulty. And you'll see this is important when we do the stochastic scheme as well. So what I'm interested in is showing that xk plus 1 minus x star is bounded by q raised to k times x naught minus x. Okay. So what I'm going to do, there's a typo in the very first line. This should be xk plus 1 minus x star squared. Okay, that's obvious. Okay, so this is equal to the projection of, by the update rule, and we know that by the definition of x star is okay, is that clear? Now we can use something called the this is why I like to do this on the board. An operator is said to be non-expansive when the following holds. For all uv. If is non-expansive, and it is. The projection operator can be proven to be non-expansive. What that means is if you take two vectors, so what is the intuition for non-expansivity? Let me show you what it is, okay? If I give you a set and I give you 2 points, if I project this point on this set and this point on this set, this is the projection, u, v. So this distance is always less than this distance. So such projectors, such mappings are called non-expansive mappings. After you apply them, the distance between the images reduces. Okay. So now what that does is you can write this as xk minus gamma k f of xk minus x star plus gamma k f of x star. And I'm going to say this is by non-expansivity. Everybody with me? Okay. So then what I do is I have xk minus x star minus gamma k f of xk minus f of x star squared, which is equal to xk minus x star squared plus gamma k squared. So now what do? I just open this out. Norm a plus b squared is norm a squared plus twice a transpose b plus norm b squared. So this is gamma k squared f of xk minus f of x star plus 2 gamma k okay. Everybody with me? I've just opened out that expression. Now what I do is this, because of Lipschitz, is less than gamma k squared L squared xk minus x star squared. This, sorry, this should be negative. This is greater than eta times xk minus x star squared because of strong monotonicity. Because there's a negative outside, it's less than 2 gamma eta k. Which is then equal to 1 plus gamma, sorry. Okay, and that's the result. Okay, so you can see it's not a difficult result, it's a relatively short result, which implies that if gamma k is equal to gamma and 1 minus 2 gamma eta plus gamma squared L squared is less than 1, then you have that xk plus 1 minus x star is less than q raised to k x naught minus x star squared, where this is defined as q. This just means defined as. Okay. Okay. And just so that you can prove this, it's easy to see. If gamma k is taken out common, you get 2 mu minus gamma k over L squared. For this to be non-negative, you need gamma to be less than 2 mu over L squared. It means that this is greater than or equal to 0, which means this is less than 1. Okay. No, actually this should be, I should be careful about this. This is, sorry, this should just be directly, if this is greater than 0, this is going to be directly less than 1. Okay. You don't need this 1 minus, this is not correct, just 1 minus, it's 1. Okay. So now as, if you take k to infinity, what happens? If you take limits on both sides, you know that this is something greater than or equal to 0 because it's a norm. It's bounded by something which is q raised to k times something. This is some constant because x naught is a constant, the vector you started with. What happens to q raised to k as k goes to infinity? Q is less than 1, so what happens to q raised to k? 0, right? So then this just becomes 0, or xk converges to x star, sk equals to infinity. Okay?
Just a small question.
Mhm.
Does this true for x to be convex?
Yeah. So what did we do? So any kind of nastiness that you had, remember we talked about this at the outset. This was, oh, I didn't have it here. When I wrote out the problem, I had the capacity constraints, I had all those constraints, and they were part of the projection. So what is the projection operation? The projection operation is, once I compute xk minus gamma k, I just need to solve w minus xk minus gamma k f of xk squared, where w lies in this set. That's the projection problem. You remember the projection problem, right? You have a set x, I'm here, I just need to project. It's a quadratic program, strongly convex quadratic program. In a lot of cases, it's easy to solve directly. You can get it in closed form. If you have non-negative, if you have an interval, lots of those things you can just get a direct max min type thing. So, is this clear? Okay, so now the linearly convergent algorithm is like our gold star. Okay, you're not going to get much better than that if you're working without second derivatives. You're working with second derivatives, you can actually get quadratic convergence, which is faster than linear convergence. Okay. Now, what happens when you lose strong monotonicity? So you can see what happens when you lose strong monotonicity. You don't have this negative gamma eta showing up. So there are several avenues. Okay, now it's difficult for me to provide all the different. There's been work done where instead of taking the map, you can take a single step, but you have to use a reflection operation. There are different ways. Here is a very classic scheme that was presented by Karpelovich. I believe this was in the 60s or 70s, and it's called the extra gradient scheme. The extra gradient scheme allows you to deal with monotone maps, but it requires two projections. So let's see what we're doing. In our first projection, we do exactly what we did before. Okay. The second projection uses the value of the first projection in evaluating the map, but uses the initial iterate to start. Okay. So let me draw that so you have an understanding of what it means. So if this is the map, so this is the set, actually I don't want to put contours in it. So what happens is, suppose you start here, your first step, this is xk, you move along this direction, you project back. Okay, so now this is xk plus half. Okay, now what do? You compute the map here. Suppose the map is taking in this direction, you move it here, and then you move this way, and then you come down, and that's xk plus 1. Okay, so you would have moved like this, but instead of that, you move here in that direction. So you use the new point to get a direction, but the old point to start, and again project on. Okay, that's the extra gradient. It's a slight change, but that change buys you a lot. Buys you the ability to actually prove convergence for a weaker class of mapping. So it's a big step, right? It's a big step, yeah.
I don't see a difference with the
You don't see a difference? So this first step is like the previous step. The second step, so this is not, previously you just took one step at a time. Here you take two steps at a time. The second step takes xk plus half to update the map, and the previous step, the initial iterate, to decide from where you're starting. Okay. Now, one of the problems is that when you have a variational inequality problem that is monotone, it has multiple solutions. So when it has multiple solutions, the notion of xk minus x star is not, it's not well posed, because I don't know which x star I'm looking for. So the way we get around that is to use something called the gap function. The gap function is a merit function that captures whether a point solves the variational inequality problem or not. Now, if you have a convex optimization problem where the function is not strongly convex, that can have multiple solutions as well. But we use the function value as a metric of how the algorithm does in optimization. In variational inequalities, there is no standard metric that you can use to assess the behavior of the scheme. There's no cost function that we can look at. Now, if there's some magical situations where we can convert to an integrable problem, maybe there you can do it. But more generally, you don't have anything. To this end, the gap function was developed. So the gap function is a function that is associated with the variational inequality and has two properties. A, it is non-negative, it is restricted in sign, so it's either non-negative or non-positive, and it's 0 if and only if x is a solution to Vi of xf. Okay, but remember, it's not convex, not necessarily, right? So if you're thinking, hey, I've got this function, I'll just optimize it. Bad idea. It's a non-smooth function, right? So you can't mess with it too much, right? So you're only using this function to evaluate the progress of the algorithm. Okay, so just it's a way to track the algorithm. How's the algorithm doing? Okay, so we provide rate statements in terms of this g of x. Okay. Now, here is one gap function. So this gap function basically, wherever you see supremum, just say maximization. So it's the maximum of y over x of fy transpose x minus y. So if you give me an x, I just need to solve this problem. How difficult is this problem? Can someone tell me how difficult this problem is?
It's nonlinear.
It is nonlinear. It is nonlinear. That's what I mean. It's not an easy problem, right? In general, to evaluate it is not easy. But remember, we're not going to be using it to update the iterates. All we're doing is we're going to be using it to assess the behavior. So at the end, you can just use this to check. So Vladimir is right. This fy is a map, right? It's some function of y, transpose x minus y. So if fy is an affine map, then the problem is quadratic. Okay, if fy is nonlinear, it's nastier. But remember, I'm never actually solving this. I'm not, I may just evaluate it somewhere, but that's all I'm doing. Now I'm going to show you another gap function, which is a little easier before I proceed. So there are two types of solutions of VIs. There's something called a strong solution, which is the one that we've been working with. See this thing on top? That's the strong solution. So it's a solution such that f of x transpose y minus x is non-negative. That's the one you've been seeing. A weak solution is y minus x transpose f of y. Okay, so when f is monotone, every strong solution is a weak solution. When f is continuous, every weak solution is a strong solution. So when f is continuous and monotone, that's what we're looking for. Strong solutions are equal to weak solutions. Why is that important? It's important because, hang on. Just hang on a second. I want to just see which gap function I used. Yeah. I forgot to put, I forgot to just state that. Let me just state it here. So the one line, I don't know why it seems to have my typesetting. So when you have, so there is something called, so you saw that gap function. So there is a gap function associated with the weak solution, and it's called g of x, is defined in this form. It's called GW is the supremum of y, and it's going to be X transpose Fy minus X. Sorry, no, what is it? Yeah, y minus x, suppose f of x. Yeah, exactly. So now this gap function is only linear in y. Okay. So this is useful both in terms of evaluation and in terms of computation if you need it, but we don't use it. We just use it for analysis. Okay. So this proof, because it's a longer proof, it's going to be hard to keep track if I write everything on the board. So let's do it slowly, make sure that we go through it because it's a longish proof.
Before
Yeah.
could you please give us some insight on what is actually the meaning of the weak solution?
So the weak solution is exactly, I mean, there's no, it's just that it turns out that when you have continuous maps, if you, so when you looked at for y minus x transpose f of x is non-negative, this was an equilibrium criterion. It turns out when the mapping is just continuous, this is also guarantees that this is a solution. Okay. Now the thing is that when we are working with continuous and monotone maps, in general, what you can do is these solutions these solutions coincide. A weak solution is a strong solution if it only if. But in general, the solutions to one and the other are not the same. So if you're looking at monotone maps, we're interested in strong solutions, and there are weak solutions that are not strong solutions. Okay. Similarly, if you're interested in continuous maps, weak solutions, the set is smaller. So think of it as a modified problem, which gives you another solution. It turns out these solutions coincide when the map is continuous and monotone. So in which case you can use either definition or either a solution. Yes.
Can you say what is B X W star?
XW star is a set of solutions that satisfy. Hey, there's a typo here. This should be W. Okay.
And big X star
Is the set of that.
It's not.
It's the true solution set. I mean, not true. It's a strong solution set.
It's not related to a dual set or.
No. It's X star. I'm sorry. That's notationally a bit of a nightmare. But yeah, it's just nothing to do with the dual cone. It's just a set of solutions of the VI. Okay. So let's start by trying to prove this. Same requirements. The only difference is that I need that the map F is bounded. For any x, I know an upper bound on the value of the norm of f of x. Okay. I need that the map is Lipschitz, but not necessarily strongly monotone, but just monotone. Again, same idea. We start with xk plus 1 minus x star squared. What do we know about xk plus 1 minus x star squared? It can be written as a projection of xk plus 1, or the projection of xk minus gamma k of f of xk plus half on the set by the definition of the update rule. Okay. Is this clear? Minus, now remember what x star is. X star can be trivially written as x star is just equal to the projection of x star onto the set. Why do I do that? It's just a trick so I can invoke non-expansivity. Because if I have the projection of the difference of the projection of two vectors, I can write it as in this form, and I'm going to show you. Okay. Actually, I don't need to put the projection here. I apologize. I don't need the projection. I just keep it as x star. That was a mistake I made. No, it's not a mistake. It doesn't change because this is equal to x star. I thought I would need to go in that direction, but I don't need to.
Because X star is in the cone?
No, x star is in the set. Yeah. Yeah, but I didn't need to do that. I can just stick with it here because I used a different avenue. I didn't use non-expansivity. See, so all I've done here is I've just stated the update rule. Next step, I add and subtract yk. This is yk. Okay, and then I open it out. So I get pi of x of yk minus yk the whole squared plus yk minus x star the whole squared plus twice the projection minus yk transpose yk minus x star. Okay, is everybody with me? Christy? Yeah? Anna? Isan, is it clear? Okay. So now, next step. Let's look at this expression on top. What I'm trying to do is I want to get a bound on this. Okay. So now, if I look at this expression, this is 2 norm pi of x yk minus yk the whole squared plus twice, there's an extra plus here, sorry, plus that expression. Now what you notice is you can add and subtract the projection of yk. And if you look at this, what is the projection of yk minus yk transpose yk minus the projection? So what that is, yeah, so what you get is if I pi of x yk minus yk transpose yk minus the projection. So this is the negative of this vector. So it's like saying 2 times x transpose negative x. So you can take the negative out, you get minus 2 times norm x squared, which is pi of x yk minus yk squared. Okay? So that's the first term that you get. Right? That becomes this negative 2 pi of x of yk minus yk the whole squared. Let's look at the second one. You just get pi of x yk minus yk transpose pi of x yk minus x star. Now look at this. This term and this term are the same except this is plus 2 minus 2. So this disappears. Okay? You can cancel that. You're left with 2 of pi of x yk minus yk transpose pi of x yk minus x star. Bless you. Now, the last inequality follows from the projection inequality. Remember we did this in 2 lectures ago where we said that if you have a vector that you're projecting onto a set, if you're projecting a vector onto a set, so this is x, this is projection of x, and this is y. What do we know? We know y minus projection of x transpose x minus projection of x is is less than or equal to 0. The angle is obtuse. Okay? And that's exactly what I have here. Okay? Okay. So as a result, what we've shown is this is less than or equal to 0, this whole thing. So if this is less than or equal to 0, if I take one of these, there are 2 here, right? This whole thing is less than or equal to 0, I can take one of these and move it to the right side, I get a negative here. Hooray, is that clear? Okay. So does everybody see how I've shown that this expression is bounded by negative this? Okay. So the next step now, so remember what I'm trying to do, I'm trying to bound this guy here. So now I substitute this recursion to obtain the following. So I had this from the previous slide, and now what I do is these terms 2 and 3 can be bounded by the negative of that. Okay? Just from the previous slide. Okay. Now what I do is I just write out the expression. This should be yk. What have I missed? Pi of x yk. I screwed up something. Hang on a second. What did I do? Oh, no. So this yk minus x is here. Okay, fine. I was wondering, did I make a mistake? Okay, so I have xk, I have this term. And so what is yk? Yk is xk minus this guy, and x is just this. And this is this. Okay. Now what do? I just open this up. You can see there's an xk here and xk here. You see they're going to cancel. If I open this up, I get xk minus x squared, gamma k squared norm f of xk plus half squared, minus 2 gamma k xk minus xk minus x transpose f of xk plus half. Repeat the same thing and I have an xk plus 1 minus xk here, okay, minus gamma k squared f of xk plus 1 half squared plus 2 gamma k, because there was a negative sign outside, xk plus 1 minus xk transpose f of xk plus half from here. Okay, so now the first thing that you notice is these two cancel. From this, xk transpose f of xk plus half and xk transpose f of xk plus half cancel. You're left with xk plus 1 minus x transpose f of xk plus half. This expression. Everybody with me? Farzana? Clear? Tariq? Vigorous yes? No? No, tell me which part. We'll slow it down. So, were you okay with from here? So when we started, we had the update rule. You apply the update rule. So what was xk plus 1? Xk plus 1 was just this. Your first step is to say, I know what xk plus 1 is. Let me introduce that. So I introduced that. So I replaced xk plus 1 with this. X star, we know x star is the same as a projection of x star onto x because x star lies in x, right? Step 1. Next step, what I do is, actually I didn't need the projection, I'm sorry. You add and subtract yk. Nothing has changed, right? And then I just use the fact that this is like a plus b the whole square. And what is the expansion of a plus b the whole square? A squared plus b squared plus 2ab. In vector form, it's norm a squared plus norm b squared plus twice a transpose b. Okay, so then when you write that, you get these expressions. I spent some time showing that this plus this can be bounded. See, this plus this. So this plus this can be bounded by 0, which means I can take one of these to the other side. So I get this expression. Okay, so that was the second big step. Questions? Emily? Clear? No? Good. Fabio? Okay. So then I utilize, so I have this plus this. I bound that, I get a negative here. Then I just open these up. I expand them, and I expand them by substituting yk. What is yk? Yk I defined here. Xk minus gamma k times f of xk plus half. I expand it in both cases and I write out the expansion. Two terms cancel and I'm left with this. Okay. Now we're not too far away. Okay, so we have this. Now all I do is I add and subtract. I have f of xk plus half. So I have f of xk plus, hang on a second, what did I do? Xk plus, I should have an xk there. This should be xk. So I added and subtracted xk. So this was, so this was xk. This was x. I added and subtracted x. I don't know why I made this x star, that's not correct. So this should be here. I added and subtracted xk. So minus, this should be xk here, and this should still be x. Okay, this stays here, that's fine. Now let's look at this guy. So when you have twice gamma k xk plus 1 minus xk transpose f of xk plus half, how do you expand that? What is the expansion for this 2ab? It's less than what? Anyone can think about what 2ab is less than? It's less than a squared plus b squared, right? So in our case it's a vector, so it's less than norm a squared plus norm b squared. So in this particular case, this term minus 2, so minus 2ab is ab is also less than norm a squared plus norm b squared. So this is less than norm xk plus 1 minus xk squared. Remember this was xk, this is a typo, plus gamma k squared norm f of xk plus half the whole squared. And you're left with this term at the bottom. Now, why is this helpful? Because now look, you have a minus and a plus, and you're going to see these cancel out. And you're left, and now you had xk minus x. What I'm going to do, there was an f of xk plus half. I'm going to add and subtract f of xk. Okay? I'm nearly there, and the reason why I'm there is because this looks a lot like the gap function. Okay? So now I'm just going to analyze term A. So this term A okay, so the term A, 2ab, this is gamma times A, there should be a transpose here, transpose B is less than A squared plus B squared. Now, what do we use here? What is this? I've used Lipschitz continuity of this map. So f of xk minus f of xk plus half is less than L squared times xk minus xk plus half, the whole squared. Okay. Now, what is xk plus half? Xk plus half in this particular case is xk minus gamma k f of xk, and this is xk. Why is that? Does anyone remember? How did I get that? Just so that, let's remind ourselves. So there are some jumps which I want to make sure everybody gets. Xk minus xk plus half is the projection of x on xk. Xk is always feasible. Projection on xk minus gamma k f of xk. We can use non-expansivity and you get xk minus xk minus gamma k f of xk, which is equal to the xk and xk cancel. You get gamma k squared norm f of xk squared. Okay. There was a L outside, so you get L squared gamma k squared f of xk squared. So what that means now is, from the previous expression, you're able to bound everything in terms of xk minus x the whole squared, gamma k squared times this, gamma k squared times xk minus x the whole squared, plus L squared gamma k squared, and this is the one term that you have. Now, I'm going to take this to the left side and take this to the right side. So I have gamma k xk minus x transpose f of xk is less than xk minus x the norm squared minus xk plus 1 minus x, because this has been taken to the right side, plus everything else. Okay. Now, what we know is, on the left side, because of monotonicity, xk minus x transpose f of x is less than xk minus x transpose f of xk, just from monotonicity. Because what does monotonicity tell us? F of xk minus f of x transpose xk minus x is non-negative, right? Now, what you do is, if you sum this up, if you sum this up over all k, what happens? If you start from k equal to 0, this is 0 minus 1, 1 minus 2. If you sum them up, you just get x0 minus x the whole squared minus xk minus x the whole squared plus all of this sum from k equal to 0 to k minus 1. And that's what we get. you get 2 gamma k xk minus x transpose f of x is less than f of x naught minus x the whole squared minus xk minus x the whole squared plus a summation all of this, which is weighted by gamma k squared. Okay. Now I'm going to define the averaged iterate. We often do this in optimization, that if I produce an algorithm, I can't make a statement about the output, but I can make a statement about the averaged output. So I take each iterate along the way and I keep building this average. So after 2 steps, I have x0 plus x1 over 2. After 3 steps, I just update that to the previous average, multiply it by 2/3, add the new iterate, and divide it again, right? So I can show that this is x bar k. So look, I've got that, right? Now I divide the whole thing by summation of gamma k. If I divide by summation of gamma k on both sides, I get this. And because xk minus x is non-negative, I can bound it away. Okay. Now that I've got this expression, all I do is, if I take the supremum in x, I've basically got the gap function in terms of xk. Okay. So that gap function is less than something divided by summation of gamma k. So if I pick gamma k to be gamma, I get c squared over something over k gamma plus b gamma. So if I choose gamma as square root a over bk by just minimizing this, just calculus, it turns out that the gap function diminishes at the rate of 1 upon square root k. So that's the rate of convergence. And as k goes to infinity, the gap function goes to infinity, 0. Okay. So I know it's a longish proof, but the goal of the proof is not that I don't expect you to go back and, I'm sure you'll have dreams about this proof because it's something that you can't get out of your mind. But if it does happen that you forget it, what you want to just remember is that for monotone problems it's a little harder, and the techniques we've used are something you want to keep in mind. We've used non-expansivity of the projector, right? That's something that is quite useful. We've used monotonicity of the map to bound on the left. We've used an averaging structure to so that we can basically get rid of intermediate iterates, and we've used a constant step length which we've chosen by optimizing a bound. Okay, so I don't expect you to sit and remember the proof. That's not the goal. We've got a lot that we cover. I don't expect, but what I do hope is that you remember how we went through it. The way we went through it was we started with the original recursion, and it is a lot of steps. It takes time, right? I mean, it's a longish proof. But the idea is to just start from the definition of the update rule and then try and figure out how to get rid of or simplify each of the terms to the extent where you know which terms you can deal with and which terms you can bound away and which terms you can manage in the end. So if you have terms which are of the order of gamma squared, those are fine. If you have terms which are order gamma, you need to deal with them. And if you have terms which are constant, you have to get rid of them somehow because they'll add to the error. Okay.